Yep. So yeah, it's a spin restricted non-adiabatic coupling data converted to the Redfield matrix and also visualized. So some of the important equations are listed down below and also on the next slide. So in order to do the conversion from the data to the Redfield matrix, you'll need three input files. You need, well, three types of input files. You'll need all of your coupling files, which we talked about in the last or 2 meetings ago, how to obtain, and also previous talkers already mentioned that as well. You'll need the energy pop files, also mentioned in the last talks and last presentation, and then you'll also need a correlation script. I think there are a couple different versions of this. The one that I used is the correlation underscore v7.m. I made a couple modifications because, and I'll point them out in just a second here too. The script was getting mad at me, so I had to change a couple things around. But for each individual system that you're doing, there should be a few different things you're changing depending on the data for your system. I've got those different areas that you should be changing highlighted with these three boxes. So in the green box, you should just be changing the value of your HOMO, the lowest orbital in your energy pop, and then the highest orbital in your energy pop for Omin and Omax respectively. My energy pop is only 60 orbitals, so I just included them all. And then after that, the thing you should be changing is in this for loop, you should be changing the loop to go between all of their coupling files. And so I had from 0 to 300 here. And just below the red box are a couple things that I had to change around to just get the script to stop yelling at me. I had to add, so for between the 0 and 100 coupling files, it kept just putting K at the end. It didn't have the leading zeros that my coupling files have, so it'd be like 003, 004. So I had to add that just to get it to stop yelling. And then also, since I started mine at 0 and not 1, that line that creates the C array yelled at me because you can't have a 0 dimension in the array. So because that N was originally the K, so I had to add that N as well. Just little things. You might have to change that, might not have to, but figured to point it out. But then the thing you probably will have to change in the blue box is the times that this is going over. So it should be from the number of coupling files you have minus 1 should be the total time steps, and then time 1 from 1 to 1 minus your total time steps, and then time 2 is from 1 to, or time 1 to your total time steps, so 300. And then that should be really all you need to change. The rest of the code is that I'm not displaying here. There's more code that I didn't include here. That's just creating figures for the most part. So it's not something you really should need to mess with. And the other stuff in here, it's just things that depend on the data we just talked about entering. So you really shouldn't need to mess with those either. Any questions before I move on?
Yes.
Yep.
Would you please, can you draw on your screen? Same as you connected this parts of script with the arrow. Can you draw as we go?
I'm not sure how I do that.
Maybe try some annotation mode.
Is this doing it?
Yeah.
Okay, perfect.
Excellent. So would you please connect equations and the code, specifically what corresponds to time 1 and time 2 in the equations?
Oh shoot, I just lost the annotation, I think. I can try. I'm not exactly sure I know which ones they are, but I believe that hold on, I need to look something on my screen. Okay, yeah. I'm not exactly sure which ones are connecting to which.
Just try.
I think this.
It sounds like a trap, but I'm sure you can climb out of it.
I think that connects to there, and that one probably connects to that one.
No. Let's focus on the time. So in the code, you have time 1 and time 2, right?
Yep.
And in the equations, you have t, tau, and t plus tau.
Oh, I see what you're saying. Yeah. So yeah, time 1 would be tau, and time 2, I believe, would be t plus tau.
I would agree with this. I would agree with the second, that time 2 is t plus tau. But what is time 1?
I mean, sorry, yeah. Time 1 is t, not tau. There you go.
Okay.
Is that correct? And
then time 2 is
would be t plus tau.
Okay. And what is tau in the code?
Is that just a time step?
What else? Can you look in the line with CORR inside the cycle? Lower, lower. So we move lower, lower. This line, upper, upper, upper. Yeah, this line. See correlation. Yeah. So what would correspond to tau in this line?
Tau would be time 1 plus 1.
Time 2 minus time 1. You can circle it.
Okay.
And call it tau. Yeah. Okay. Okay. Yeah. And it is not the last question. Now, in the equation you have V and AC evaluated at t plus tau and t. So what corresponds to this symbol V in the code? And you do not you cut the line, but
yeah,
we all remember what it is after. So yes.
Is it here?
So this C symbol will be V, corresponds to V, right?
Yep.
Okay, very good, very good. And then as line in the code continues, if you multiply to C once again, so it will be C squared, or C evaluated at different times. And they evaluated at different times that are offset from each other by tau. If tau is small, they are the same, they are correlated. As tau increases, they become random to each other and cancel, interfere destructively, therefore correlation function drops. Okay. So can you guess what is next line? ECORR. And without continuing the line, it's quite hard, but in the line for CORR, it's just a product of C at time 2 times C at time 1.
Okay.
And at second line, ECOR, it multiplies C at time 2 times C at time 1 times exponential in the power minus imaginary unit frequency and multiplied by difference of time 2 minus time 1. if you remember the code. And I think
Mm-hmm.
K in the previous talk was showing the line completely.
Yeah. Yeah. Sorry, I cut that off. I didn't quite have the room.
So how would you characterize this CORR and ECORR corresponding to equations?
So if CORR is referencing to this equation, that's the correlation function. And if ECOR is related to this one, this is giving us the Redfield
yes,
matrix.
It would correspond to Fourier transform of correlation function.
Okay.
Which is a Redfield. But since the couplings are not correlated, since correlation drops instantaneously, this exponential is evaluated only at time equals 0, and e to the power 0 is 1. So in many cases, this M and R correlation function and its Fourier transform are very close, just because it's quite random process. Whew. Sorry for interrupting you and setting up prep. So please
that's all good. 1 second. Okay, there we go. So after you run that code, and get rid of these annotations, you'll get several output files. You get quite a lot, but there are a few that are you kind of just want to pay attention to. So the most important one is the RRR file, which is the Redfield matrix file, which describes the rate of transitions between states. And then you'll also get a bunch of figures that visualize this Redfield matrix, which is great because visualizations are nice. You'll also get a lot of intermediate files that are kind of the steps along the way that you shouldn't really need to pay attention to unless something's going wrong. But I don't think you'll have to have much use for them. And on the next slide, I've got a few more examples of some of these output files. You can see that you're getting kind of what you expect, that along the diagonal, which would indicate a transition from a state to itself, you are getting 0 because that shouldn't be a possible transition, whereas transitions close to the diagonal are very often relatively strong because they're transitions that happen fast. And then the one other function you want to look at is the autocorrelation function, which the other presenters have already mentioned a bit, which kind of indicates how well your function or your system is behaving. If this drops off quickly and approaches 0, you should be in the clear. If this is staying oscillating quite high, something might have gone wrong in your simulation, or it's just not behaving right. And that is all I have.
Okay, please join me in thanking Boston. So presentation is open for discussion. Although we had some discussion during the what slides were showing. So any constructive criticism?
So I have a question.
Please.
So thank you, Boston, for your presentation. So this autocorrelation function you mentioned just for double checking this point that simulation is running well or everything is correct, or it can provide us any insight into, I don't know, some optoelectronic properties of the system.
Yeah, I want to be honest, I don't have the entire knowledge base to answer that question fully. I'm not sure if the autocorrelation function will tell you or give you any indication about any of the other properties. The limit of my knowledge is that a quickly decaying autocorrelation function shows that your simulation or your system is behaving well. That's about the limit of my knowledge. Someone else, Dr. Kill and Aaron, might be able to answer that question a little bit more in depth.
Thank you.
So if autocorrelation function oscillates and doesn't decay to 0, it's not the end of the universe. It means that one needs just to be a little more careful and precise. So right now, the code that we practice has a very, very strong approximation. We assume that due to this rapid drop, that Fourier transform basically equivalent to autocorrelation function itself. So we take only 1 point out of this stuff, but and it is safe in the RRR. If it would oscillate for a noticeable amount of time, then we need to process not CORR but ECORR, this Fourier transform function, and it will, and then we will save, store Redfield based on the Fourier transform, and it will be fine. The trick that applied right now, the approximation, is just made to make it as simple as possible. But oscillating correlation functions can be converted from the time domain to frequency domain through Fourier transform, and it is not it's not a big deal. It's already included in the code. It's just commented out and not used. It's possible, but in most of practical examples, it is not needed. This will be needed for very, very small systems with few atoms. Like here, Boston is exploring system with about 10 atoms, and we see that it drops to 0, not in 1 femtosecond, but maybe in 10 femtoseconds. If one would take system of like 2-3 atoms, it will decay a little longer. Okay.
Thank you.
More comments to Boston? Critical suggestions? More comments 1, more comments 2, more questions 3. If no, let's thank Boston once again.